When we talk about thermal energy, the very first thing we need to do is differentiate between three very similar terms that in physics technically mean different things. So when we actually say thermal energy, we mean the total kinetic and potential energy of all the atoms and molecules in a substance. But you can imagine that might be incredibly difficult to actually calculate. If we wanted to know total thermal energy of a substance, we would need to know information about every single atom and molecule in that substance. And in most cases, that's incredibly difficult, if not impossible to do. So usually we don't actually track the entire thermal energy of a substance. We talk about two other related concepts, heat and temperature. Heat is just a special term we use to mean energy being transferred in the form of thermal energy. And we will talk later about how this is always occurring from a warmer body to a cooler one. So heat really just means a transfer of thermal energy. And temperature is a way that we can actually track differences in thermal energy. We're not tracking the total kinetic and potential energy, but what we're doing is getting a measure of the average kinetic energy of the atoms and molecules of a substance. And that's something that we can measure and track even if we don't know specific information about every single atom and molecule. So make sure you're understanding that those are three different concepts. When we talk about thermal energy, though, it's useful if from there we talk about what thermal energy depends on. So first off, one thing that's sometimes forgotten about is that mass also has an impact on thermal energy. If you have a greater mass, you have more particles involved in your substance. And so those particles then have a greater collective kinetic and potential energy. So what I'm trying to say is that an increase in mass, or a greater mass, that's what my up arrow means, leads to an increase in thermal energy. The follow-up to that is the more obvious thing that we should already understand. That of course when something's temperature rises, when that average kinetic energy increases, that of course means that the total thermal energy overall must be increasing. From there, it's useful if we talk about the three different ways that thermal energy can be transferred, or in other words, three different ways that heat can be transferred. And you have some written definitions on your page, but I've just got a more visual representation of it here for you to see. And this is a way to show all three of them all in one simple diagram. So first off, conduction is usually something that relates to solids. So when we look at conduction here with the fire poker, what we're seeing happen is that this end of the fire poker is very close to the heat source. So the atoms at that end of the fire poker are going to start to move faster because an increased temperature means faster moving particles, more kinetic energy. But when those particles move faster, they're going to start to bump into the particles right beside them. And so that's going to cause some particles a little bit farther down the line to get bumped into as well. And they will start to move a bit faster because of that. So that bumping of the particles allows that heat energy to actually transfer down the line of the fire poker. And so that's why holding even the very far end of the fire poker where the glove is, you would still feel some heat, some warmth coming from the fire. It wouldn't be nearly as hot as the end that's close to the fire, but some of that heat would transfer down the line because one particle bumps into another, which bumps into another, and transfers that energy in a chain reaction all the way down the fire poker. So that's conduction. And it's really just a bunch of atoms bumping into each other and causing other atoms beside them to move faster. What's very similar to that, and it's almost really the same category, is something called convection. Convection is really technically the same as conduction. It's still atoms bumping together and causing other atoms to move faster because they bumped into them. But we give it a different term and call it convection when we're dealing with things that can flow, specifically liquids and gases. Because when things can flow, they're able to move much more freely, and we see the transfer of energy happen a little bit differently. Specifically, it's convection that causes warm air to rise. That's what you're seeing right now. So the warm air right on top of the fire is the warmest air around the fire, because all of the air particles just on top of the fire are actually rising. The reason why the warm air particles rise is because when the atoms bump together and they're warmer, they're going to be moving faster. As they move faster, they collide with each other even harder, and that causes them to naturally spread out. When things spread out, they become less dense, and less dense materials tend to float on top of more dense materials. So the warmer air is trying to spread out and float on top of the colder air below. So that's why warm air tends to rise. And the reason why it does is what we call convection. The other form, though, radiation, is very different. Radiation actually doesn't require a medium, and a medium is just another word for a bunch of particles. So remember, with conduction and convection, it was all caused by actual particles bumping into other particles, and that's what transferred the energy down the line. With radiation, the energy is able to move without any particles in the way whatsoever. Radiation specifically is actually what we call electromagnetic radiation. So visible light is one example of that, but also ultraviolet and infrared radiation are other examples. X-rays, microwaves, radio waves, those are all actually the same kind of energy in physics. They're just different amounts of energy. But they're all versions of what we call electromagnetic radiation, and those are able to move through space actually just because of very quick fluctuations of something called an electromagnetic field, which we'll talk in a lot more detail about in our final unit. So for now, just try and understand that it's different from the other two and that it does not require any particles to transfer that energy. In other words, it does not require a medium to transfer that energy. I've included this picture partly as a way to demonstrate all three of those methods of heat transfer once again, but also just to provide a little bit more context about some things that convection can do. So it doesn't only cause warmer things to rise above colder things, it can also set up a pattern called a convection current. So if I look at the water here boiling on the stove, one thing we know is that these molecules of water towards the bottom of the pot are the things that are going to heat up first. They're closest to the stove element. So they'll heat up, and that will cause them to spread out and become less dense, and so those less dense things will start to rise up. But the reason why they're actually rising up is because these water particles that are towards the top are much more dense. So as the warmer ones tend to rise, the colder ones tend to sink back down. But when they sink back down, all of a sudden they become those atoms that are closer to the bottom again. They'll warm up, they'll spread out, and they'll move back upwards. And so we get this constant cycling of moving towards the top and becoming more dense as you cool off, but becoming more dense causes you to sink back down, which makes you warm up, and that causes you to spread back out and move back up towards the top. So it's this constant cycling of being more dense to less dense to more dense to less dense. And that's what causes you to sink and rise and sink and rise. And we get this current effect where all of the water particles are actually going through a circular cycle. That's called a convection current. From there, we want to figure out how to quantify this. How do we really calculate how much heat is transferring from one substance to another? And this can get a little bit complicated depending on what substances we're dealing with. So a common explanation you might see in a lot of textbooks goes a little bit like this. Different substances require different amounts of energy to increase the temperature of a given mass of the substance. This occurs because different substances have different capacities to hold heat. So when we say hold heat, we mean the ability to absorb lots of thermal energy without actually increasing or decreasing your temperature in any way. So for example, if I wanted to warm up 1 kilogram of glass by 1 degree Celsius, that would take me about 840 joules. But if I wanted to warm up 1 kilogram of water by 1 degree Celsius, that would take me over 4,000 joules. So almost 5 times as much energy is required to warm up a kilogram of water by 1 extra degree compared to just a kilogram of glass by 1 extra degree. Because those two different substances, water and glass, have very different capacities to absorb that heat. They absorb the heat in very different ways and change their temperature in very different ways as a result. So to quantify that, we have this new value that we can talk about called the specific heat capacity. Specific heat capacity, which we'll give the letter C to represent it, it's just a measure of the amount of energy we would need to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. And because of that, we literally measure it in a unit called joules per kilogram degree Celsius. So it is literally the number of joules of energy we would need if we wanted to take 1 kilogram of something and raise it by 1 degree Celsius in terms of its temperature. That's what we can use to help us find how much heat is being gained or lost when we start to pump energy into some new substance. Now, when we calculate that amount of heat that's being gained or lost, even though technically it is a form of energy, for historical reasons we actually typically don't use an E to represent it. We use the letter Q when it's specifically heat capacity, or when it's specifically heat that we're gaining or losing. So we remember that it really is just energy, but we're going to use a Q to represent it. So if we want to figure out the thermal energy that something is gaining or losing in joules, we can arrive at a fairly simple formula. It's just going to be what we call mc delta T, or in other words, the mass of the substance in kilograms. The delta T part means the change in temperature in degrees Celsius. And then along the way, we also need to multiply by that special value of C, that specific heat capacity value. And when we put all of that together, we actually get an answer in joules. And it tells us how many joules of energy have been put into a substance or have been released from a substance. We can actually use the same equation for both. If we want to then do a quick unit analysis about what's going on the right side of that equation, we can break down what all the different units are individually. So the mass, of course, is going to be in kilograms. Then we're going to multiply by specific heat capacity, which had a very strange unit. It was joules per kilogram degrees Celsius. And then we multiply by a change in temperature, which we're going to measure in degrees Celsius. So this might allow you to see partly why that specific heat capacity has such a strange value in the first place. Because from there, we can do a little bit of cancellation. So the mass part in kilograms gets divided away by kilograms being on the bottom of the specific heat capacity unit. The degrees Celsius also gets canceled away because of the degrees Celsius on the bottom of the specific heat capacity unit. So all that leaves us with is joules. And so in the end, this big calculation is really just giving us something in joules, which is telling us that really we have found a form of energy. Specifically, we found how much energy something has gained or how much heat energy something has released as it became cooler. Now let's try and use that to actually figure out how much energy is required to heat something up. So for example, a greenhouse we know can actually get quite hot. So on a typical day, let's say from 8 a.m. to 2 p.m. on a hot day in the summer, 24 kilograms of glass might go from about 12 degrees Celsius all the way up to maybe 34 degrees Celsius. And we want to try and figure out how much energy was actually required to do this. And what we're going to need is the specific heat capacity for glass. And you'll see me sometimes write this in a specific notation where I put the letter C, and then as a subscript, we can state what material it's for. Because every different material will have a different specific heat capacity. So the specific heat capacity for glass, in this case, is 8.4 times 10 to the 2, or about 840 joules per kilogram degrees Celsius. So let's put all of that together and see what we can solve. Always state our given value, so we know mass in this case is 24 kilograms. We know the specific heat capacity is 8.4 times 10 to the 2 joules per kilogram degrees Celsius. We also need to find delta T, which is the change in temperature, and we're not directly given that in the question. But remember, when we find change in any kind of variable, it's always some final value subtract its initial value, or what I'm going to call temperature 2 subtract temperature 1. In our case, that's 34 degrees Celsius. Then I subtract away the 12 degrees Celsius that it started at. And what I'm left with is that really we have 22 degrees Celsius worth of change. That's how much the temperature has changed. And of course, in the end, what we're really looking for is how much energy is required. But because it's thermal energy that we're looking for, thermal energy being transferred, we're going to say that it's Q we're actually looking for. So when I go to solve, I start with the original formula that I know. Q is equal to mc delta T. And now I can just plug in the things that I know. It's going to be 24 kilograms, 8.4 times 10 to the 2. Remember, that's in joules per kilogram degree Celsius. And then I multiply by the 22 degrees Celsius of temperature change that I have. When I do all of that, you should get about 4.4 times 10 to the 5 joules when we round to 2 sig digs. So that's about 440,000 joules of energy. That's how much is required to heat that glass from 12 degrees Celsius all the way up to 34 degrees Celsius. And all we needed was one simple formula to calculate that.